Hi everybody, it's Mr. Hamilton here, and I'm going to go over how to calculate the area under the VT or velocity time and the acceleration time graphs. So this is the data that I got, and you'll notice that it's covered up a little bit, but after 1.4 seconds, the data didn't, it was clearly falling off the ramp because the displacement got smaller. So I've only kept it to 1.4 seconds, and what you can see there is that my displacement, actually this is not displacement, this is actually a position time graph. I should have labeled that properly. My position time graph is following this trend that increases, gets steeper and steeper over time, and then at 1.4 seconds it's done, right? I'm not including anything beyond that. So in my particular case, it was about 90 centimeters away from where it started at 1.4 seconds. And so then what I did every time is, in order to find the velocity, I said the velocity is my displacement divided by my change in time, and my displacement was 1 point minus the previous position point, divided by 0.1 second in each case. And so once I figured out the velocity, I did the acceleration the same way. I took the two previous velocities, because it's change in velocity over change in time. So I took my previous velocity and subtracted the one before that, and again divided that by 0.1 second intervals. And so once I generated all those values, you can see that I have one less velocity than I do positions, and I have one less acceleration than I do velocities. And that's because acceleration is based on two velocities and velocity is based on two positions. So if you keep that going, eventually the next one would be something like negative, it'd be a negative number or something, because it would take the next value as 0 and assume that it would calculate it. If it has an empty box, it calculates it as 0 minus the previous one. So we can't include anything beyond that one, and then anything beyond the 1.3 seconds in the acceleration case. So how do I actually find the area under the curves? So what I do is I'm going to extend this out. I know we only had a value that went out to 1.3 seconds, but to find the area under the curve, I'm going to extend it all the way out to 1.4 seconds, right there. And then I'm going to calculate the area under this curve. Now I've set my line of best fit to go through the point 0, 0, and your line of best fit might not have been super good to go through 0, 0. So in my case, I can just use a single triangle, but you guys, depending on where your line of best fitting went through on the y-axis, you might actually have to make like a, let's say if it goes through here, you might have to make a little rectangle on the bottom and a triangle on top. Nonetheless, we know how to find the area of rectangles and triangles. So in my case, I just have a triangle, and we know that the area of a triangle is base times height divided by 2. And so we can go ahead and we can say, well, the base in this case is 1.4 seconds. The height is about 130 centimeters per second, because it's velocity on that axis. And then we're going to divide that by 2, and we get 182 centimeters, because the seconds and the seconds cancel out. So 182 centimeters. And we divide that by 2, giving us 91 centimeters. So the area under that curve is 91 centimeters, which is very accurate to what I had as my final position on my position time graph. Now let's look at the area under the acceleration time graph, because that total area should give me my final velocity. And so I'm going to extend this out here so that it goes all the way to 0 and out to 1.4 seconds, because that's what the final displacement was. So 1.4 seconds here. If I look at the area under this curve, it's not, unfortunately, a perfect rectangle, so I'm going to make a triangle here on the top and a rectangle below it. So we'll call this the area of the rectangle, and then we'll call this the area of the triangle up here. And so the area is the area of the rectangle plus the area of the triangle. Well, we know the area of a triangle and rectangle. We know this is length times width. We know this is base times height divided by 2. And so for this rectangle, you can choose what you want to be length and width. I'm going to let the length be the height of the rectangle. It looks to be about 85, and that's units of centimeters per second squared. So 85 centimeters per second squared. And then we're going to multiply that by the width of 1.4 seconds. And then we're going to add the triangle here. And the triangle's base is 1.4 seconds. The height of that triangle goes from about 85 to 100. So in my case, it's about 15 centimeters per second squared. And then we're going to divide that by 2. So let's see what we get when we do the math on that. The first thing I want to point out is that this second cancels out with the second squared, giving you units of centimeter seconds on this part of it. And the same thing here. You got a second here canceling out with this second squared, giving you, again, units of centimeters per second. So it's giving you a velocity. If I continue that calculation, I end up with an area of 129.5 centimeters per second, which, if we go to 1.4 seconds on our velocity time graph, is almost exactly the same as we see on that graph. So if you've calculated the areas all the way out to your final time that you had for your position, using your trend lines, you should find that the area that you calculate represents the final value on the previous graph. Hope that's helpful. All the best as you finish this up.